Next. This is my biography. I'm honored to was the past president of KIST, and then now I'm the president of Gyeonggi Province, Korean Science and Technology and Societies. Next. Today I will explain about the background and then what is the ISRU, and then ISRU and then ISRI, my research institute, and then international network, and then future plan. This is a funny story. This picture in the International Space Station, myself and then Hank Rogers, my friend, and then Buzz Aldrin. Hank Rogers request to Soviet astronaut to bring his wedding ring and our picture. So our picture is in the International Space Station. Very honored. This is a BIG, Bianca Inkel's group. Go ahead. So how to construct the Mars. Okay, this one for the surviving on the Mars, we have the 8 different resources, and ISRI, my institute, is developed the 5 different level of that resources. We can use it volcano basalt, and then we can make the brick, and so we can construct by the 3D printer on the Moon and Mars. So let's explain about this. So I declare that the engineering is a too narrow area to be covered. So I claim we need to make the big engineering cover everything, not only civil engineering, mechanical engineering, and all engineering technologies to make that perform the massive project, overcome past limitation, and suggest a new opportunity. So big engineering can make that the deep sea region and desert region and polar region, everything is an extreme environment. This one is a space environment. So ISRU, we can make the resource assessment and also in situ manufacturing, and then resource processing and consumable production, resource acquisition, and in situ construction, and generation of storage of electrical, thermal, and chemical. Today, I'm explaining about the in situ construction, and also we can do the manufacturing by the 3D printer. So this 4 area is my fellow, Mr. Sanders, will present 4 different area: construction, energy, food, water, and mining. So today, today I'm explaining about the renewable materials and 3D printing, and also remote operation. So you can make it waterless concrete, which sometimes called the Lunar. Excuse me. So an additive construction, you can do all of this for using the in situ resources. ISRI can cover the Moon and Mars simulant, and then planetary structure, and entry-distant landing infrastructure, and planetary additive construction system, and moon test bed. By the way, when I was president of KIST, I prepared and then I started to construct a vacuum chamber in the KIST. I believe that Dr. Lee Jang-geun will give that information for you. So we can do the simulants and the rovers. We participate in the NASA competition and moon test bed, vacuum chamber, and structural material. Even we made the 3D printer to print that house.
If we can recycle on Earth, why can't we recycle in space?
2 minutes.
Astronauts need to recycle as much as they can if they want to survive on Mars. So wouldn't it be cool if we could take some of the materials the astronauts aren't using and recycle them to build?
This is our 3D printer, and then level 2 and of NASA Sentinel Challenge. We do the first prize out of the 77 teams. This one is we transport by the airplane. We paid $50,000, and then we don't have time to assemble the machines. But by the way, we were the third prize of that phase 2, level 3. This one is we won the first prize out of the 77 teams, and then MoonX Construction is a Korean team, Hanyang University and KIST. And the right side is we went to the competition phase 3, but we cannot bring our 3D printer. But by the way, at the same time, we make this habitat in Korea. You can see the many network here, and Bulge Aldrin is here, and then the Chris is here. We have many friends all over the place, but apparently very small starting point. Only me and my PhD student, but now you can create more and more, and then finally we won the third prize out of that 77 teams in level 3 at phase 3. So we have the international partnership today. I invited Bernard Foing, and that this ESA-ESTEC make every scenario for the future. So we got the international partnership. Not only NASA had the permission to give that 20 kilogram space for the lander, and Astrobotics, as we had a good partnership, they will give the 5 kilogram space, and you can send that 3D printer or make the brick instrument to the moon, hopefully very soon. So this one is that the younger generation. I gave that presentation, and many young generation to be not only astronauts but also space construction engineers. It is very nice of the future. Future plan is spin-off is very important. Space technology, and you can make the water extraction technology in soil, and then lunar concrete, space construction. These are all the space activities. But not only spin-on and spin-off, we can make the water production technology in extreme environment, and then we can use the polymer concrete and then enzyme concrete without heating. So enzyme is originally from ant, white ant in Australia, and we can make the brick without heating. And also we can use that volcano ash concrete. Volcano ash means that when you went to the from Earth to the moon, the transportation cost will be 1.2 million to the $2 million per kilogram. But we can use the in-source resource utilization. Volcano basalt is same content of the Earth volcano basalt. 99.5% is same content. So we can use it, volcano basalt. And also this one, we can use it in the earth. And also we can use it, develop the rover and the deep and exploration rover, we can use it. Not only the extreme environment, the North Pole and South Pole. And so we can use it, the desert exploration rover also. So we can use it, this technology on the Earth. So commercialization plan is to carry out joint research by establishing a cooperative system with emerging foreign countries and excellent institutions. So actually, if we can use this volcano basalt, and we can make the CO2 emission right, so we can get a house for 4 people. We can only get $10,000. So it's very effective and very cheap. So we can use it for the developing country housing problem to be solved. And also to share the skills and knowledge through training of human resource and exchange with foreign institutions. Not only international workshop but also symposium. To apply for patents with the incorporation, enzyme break, plastic recycling, and carbon emission trading as very important for the future. 2050, we want zero emission, CO2 zero emission, but that we can solve that problem. To demonstrate the world's best 3D printing construction technology in a short period of time in 2020, and with the aim of participating in winning the competition NASA 3D printed habitat challenge phase 3 and 4. Unfortunately, this one is many regions as postponed. And also to participate in international project, Dubai's Mars Science City project. This is also postponed because of the corona, and create future food environment too. So this one is a BIG group designed the Mars Science City in Dubai Expo. And we can solve that all the plastic, we can reusable plastic. And also with the 3D printer, we can make the house only 60 hours for one house, and many good research papers. Thank you so much for your attention, and we will discuss later. Thank you.
Thank you for your presentation. Next, the presenter gave us the video, so we will play to it from now on.
Hello everyone, my name is Kyungja Kim. I work at the Korea Institute of Geoscience and Mineral Resources and University of Science and Technology. Today I would like to introduce discovery of water on the moon and its utilization. Before we go to the main issue, that how lunar water has been found, we should check this slide first. It is important to know the nature of solar winds, which are coming from the sun, and majority of solar winds consist of hydrogen, helium, and others. These particles arrive on the moon and interact with the lunar surface materials. Have you thought about water ice on the moon? At least there are 4 cases have been recognized by the science community that water could exist on the moon because comet and meteorite can bring water to the moon. Solar wind implantation can produce water on the moon. Also, outgassing of a lunar interior such as volcanic activity contains water and releases it to the surface of the moon. And lunar core material in the giant molecular cloud includes water. I'd like to introduce discovery of water on the moon in chronological order. The Clementine mission was the first mission outside of the Earth's orbit. NASA collected almost 2 million digital images, and global maps with photo images and spectral images were made, and still compared with the other products of the recent missions. The Clementine mission firstly suggested a possible water existence on the moon based on the discovery of permanent shadow regions on the South Pole region. On the moon, ice sublimes rapidly to space, and low gravity of the moon cannot hold gases, but ice would exist in the permanent shadow regions. The PSR were identified by the Clementine mission. This was a big discovery. In 1998, Lunar Prospector was launched to find out the water existence on the moon using especially neutron spectrometer. This slide shows water maps in both North and South poles. When water is around, epidermal neutron fluxes tend to be decreased. Left side shows epidermal neutron maps, and right side shows the water maps after conversion processes. Lunar Prospector concluded that the total mass of ice on the moon is about 6 trillion kilograms. The water content is 4.68% in the North Polar region and 3.08% in the South Polar regions. Chandrayaan-1, launched in 2008, has many payloads for scientific experiment and mapping, especially MINISAR, NHEX, and SARA. Payloads have prime objective to find water ice on the moon. The Chandrayaan-1's 3 payloads confirm that water on the moon is produced by the interaction between the solar wind and oxygen on the lunar surface. Chandrayaan-1 SARA instrument found that hydrogen atoms are absorbed by the lunar regolith like a sponge and interact with the oxygen present in the dust grains. Through this process, hydroxyl and water are produced. Chandrayaan-1 had the NASA's moon mineralogical mapper. We learned that water existence on the polar regions are confirmed by Lunar Prospector. However, MCube firstly discovered both water and hydroxyl-rich materials in a very young lunar crater on the far side of the moon. An important discovery by Chandrayaan-1 is shown in this slide. MCube data shows the distribution of water and hydroxyl on the lunar surface, indicate as blue, and iron-bearing minerals are shown in the green and orange tones. As you can see in this image of MCube, the higher altitude regions have a greater reflectance features related to the wavelengths of water. Searching for water and its conformation were big issues. for the lunar science community. In 2008, Asian countries like India, Japan, and China sent their orbiters to the moon, and the discovery of water by Chandrayaan-1 followed by finding another evidence of water existence by the Alcross and Eraro missions. Weighing 3,000 kilograms of Alcross was dropped in the permanent shadow region. The targeted area was the Cabeus crater in the South Pole region. Knowing the origin of water on the moon is connected to the origin of volatiles and its utilization for future manned lunar mission. Alcross is launched with the Lunar Reconnaissance Orbiter in June 18, 2009. The Alcross is shepherding spacecraft and the Atlas V's center upper stage rocket. And this shepherding spacecraft and center rocket were separated. The center is a heavy impactor to create a debris plume. The Alcross impacted the South Pole in October 9, and 4 minutes later, collecting and relaying data were performed by instruments on board Alcross and Eraro. This slide shows the flow of the Campbell's crater where L-cross impacted. In the right side, the figure shows the visible and spectral images before and after the impact event. This slide shows a time series of images collected with the mid-infrared camera for the impact site. For two thermal mid-infrared camera images are before the impact event, and the image at time 0 seconds shows a white spot near the red arrow. And until time is 6 seconds, the mid-infrared camera image shows a white spot which is known to be water ice. In the left side image, the arrow points to the thermal signature of the central impact. This image was collected at an altitude of 600 kilometers above the lunar surface with a resolution of 1020 meters per pixel. In this image, the temperature of the white colors are approximately 35 degrees Celsius, red colors are 18 degrees Celsius, and the dark blue colors are minus 45 degrees Celsius. The right side image shows description of the observation of Lyman alpha mass spectrometer on board LRO orbiter. Right after impact, L-cross plume was analyzed by this instrument. This slide demonstrates water detection in the L-cross ejecta plume. The sky blue line is the measured water with respect to time interval after the L-cross impact. This slide shows the water observance by the near-infrared instrument. After the impact, the observance of water increased gradually until 205 seconds. This near-infrared instrument concluded that water content in the impact site is 5.6% in average, and there are other molecules such as hydrogen sulfide, ammonia, sulfur oxide, ethylene, and CO2 and methanol, etc. These volatiles can be collected when water is extracted from the polar surface regolith. In the case LRO's Lyman alpha mass spectrometer, soil mass abundance of the impact area was analyzed for hydrogen, carbon monoxide, and nitrogen, and mercury and other elements, such as magnesium, calcium, vanadium, manganese, and cobalt, and zinc, and gold. This slide shows maps of the measured and model calculated surface and subsurface temperature in the lunar south polar region. The Campbell's crater shows as a very cold area. In this region, water ice could be lost at a rate of 1 millimeter per billion years. This means once asteroid or comet is deposited, it can be hardly escaped from the lunar surface. Therefore, polar region is considered as a prime target to investigate possible locations for future lunar in situ resource utilization. I would like to mention that LRO had a neutron spectrometer to investigate the water on the impact site. The land team reported that the water content of the Campbell's crater ranged from 0.5 to 4.0 weight%, depending on the thickness of overlaying dry regolith layer. I can say that the result of land is not very different from the result of lunar prospector. This slide shows the possible landing site regions in the lunar South Pole. With the all evidences of water existence on the moon, lunar landing site candidates have been investigated as an activity of ISAC-G. For a manned mission, PSR region, water content, and sunlight, and the visibility from the Earth are considered together. This slide shows near Campbell's crater and surrounding areas of the Shoemaker craters are possible landing sites where water is available, as well as other lunar resources. This slide shows possible landing sites in the lunar North Pole region. Compared to the South Pole, lunar North Pole has much larger areas as possible landing sites where water content is greater than 150 ppm and other conditions are suitable. Last year, a very interesting scientific result has been published regarding the water cycle on the moon. Starting point of the lunar water cycle is the solar wind implantation, and the water can be produced by iron oxide in the lunar regolith and stays in the subsurface layer. This water is then released by meteorite impacts. This fact has been observed by neutral mass spectrometer of the LADEE mission. A very important message of this discovery is that possibly all areas of the moon could contain some water for humans to use for lunar base establishment. I would like to show a photo of the Apollo 17 landing site. A set of lunar samples were brought back to the Earth from this location. Especially sample 74220 has a very high iron oxide content, nearly 20%. The Apollo sample 74220 includes orange soil. This area could have been an area like lava fountain area where volatiles and gases were released. The highest population of soil size of the sample is indicated as about 30 micrometer. The chemistry of the pyroclastic gases shows water released up to the temperature nearly 500 degrees Celsius. This is very interesting Apollo data, which we could understand the nature of the landing site, and we would like to consider this type of landing site candidate where relatively more water is available. A recently published map of the lunar pyroclastic deposit is shown in this slide. The red regions contain the highest pyroclastic deposit where some water can be available on the lunar surface for manned mission in future. Water as a lunar resource is very important for an establishment of lunar base, and utilization of water will be different according to the location of landing site. This slide shows the two cases of lunar water extraction method for the polar regions and other regions. When we process lunar surface regolith, we will be able to obtain both water and other volatiles as well as minerals as byproducts. It is important for us to do this experiment on Earth as early as possible for future science and technology development toward human settlement on the moon. As a summary, I would like to say that the moon's shell may be wet, but inside is bone dry. However, we now know that there are plenty of water on the polar regions. The water can be used for human consumption and making rocket fuel to go anywhere we want to go. Indeed, discovery of water on the moon triggered humans to go a next step for lunar exploration toward lunar base construction. Therefore, many more robot missions with robots are expected before human missions. We believe that utilization of lunar resources could be feasible, and possibly the moon can be one of our travel destinations in the near future.
Planet Earth is protected by the atmosphere, the layer of air and gas that surrounds it. The atmosphere shields the Earth from solar radiation, keeps the temperature balanced, and protects us from meteoroids. On the Moon's south pole, you can see almost perpetual sunlight on the horizon. This is the site of our lunar base. Conditions on the Moon are very different from those on Earth. Because the Moon has no atmosphere, there is no protection from solar radiation. There are extreme temperature fluctuations, and there is no protection from gamma radiation, and no protection from meteoroids. The lunar lander has detached from the rocket launch and is on a course to Shackleton's crater, the Moon's south pole. Inside the lander is a cylinder which contains an inflatable dome and 2 robot 3D printers. After the cylinder containing the habitation capsule has been unloaded, a dome is inflated from one end. This provides the support structure for construction, a little like scaffolding is used to build on Earth. The lunar habitation is built by a robot-operated 3D printer. At one end, it has a scoop to collect the regolith. In the centre are the containers for the printing material. At the other end, there is a robotic arm with a printing head. The robot collects regolith from the Moon's surface. Layers of this moon dust are built up over the dome to create the protective shell. This process takes about 3 Earth months. The shell is made up of a hollow, closed cellular structure. Under a microscope, it would look very similar to the close-up of a bird's bone. Like a bone, it is light and incredibly strong at the same time. When the lunar base is complete, it can house 4 people. Inside the dome, they are protected from meteorites, gamma radiation, and high temperature fluctuations. The original capsule functions as an airlock and technical support module. The skylights draw daylight into the living and workspaces, which are sheltered within a pressurized enclosure. This method is a pioneering advance in space-age construction. At Foster & Partners, we're used to designing for some of the world's most extreme climates. We often use materials found locally to create sustainable buildings on Earth. While the Moon is an exciting new territory for architecture, the value of this logic endures.
Thank you for your presentation. Next presentation is also video is from Dr. Chang Geun-ni. We can see.
Thanks for giving me a chance to introduce space construction technologies developed by KICT, Korea Institute of Civil Engineering and Building Technology. I am Chang Geun-ni and head of Extreme Engineering Research Center. I'm going to present our research group first briefly, and then research activities in details. Finally, I would like to close my presentation with showing our future vision for lunar construction video. Main goal of this project is development of extreme environmental simulator and advanced construction technologies over TRL6 level. Our research is supported by Korean government for 9 years, and total budget is about 13 million US dollars. Extreme Engineering Research Center, E2RC, has 8 key members who mostly major in civil engineering. We also work with experts from other fields such as chemistry and mechanical engineering for interdisciplinary research. Our research consists of 2 main parts. First one is construct infrastructure for planetary surface environment, and second one is to key technologies for space construction. Why we want to construct the infrastructure is that whenever we develop the construction technology, we have to verify that developed technology in extreme environment conditions such as lunar surface condition. That's why first we build up the extreme environmental infrastructure, and then we want to develop some fundamental space construction technologies such as a space drilling system for subsurface investigation, and second one is geospatial information technologies. For planetary surface environmental simulation, we try to build up the vacuum chamber with the large vacuum chamber and small vacuum chamber connected by gate door. The large vacuum chamber dimension is 4 by 4 by 4 meter, including soil container, 2 by 2 by 2 meter, which means almost half of the main containers. The vacuum chamber is occupied by the soil container. And it's already built up, and we tested the temperature and vacuum condition. It works pretty well. I will present later. And second phase is not constructed yet. We need to first get the budget from the government. Why we need this small vacuum chamber is that whenever we want to test a device, if without this small chamber, we have to depressurize and pressurize the large chamber, means the maintenance cost is pretty high. But if the small chamber is connected, whenever we test it, large vacuum chamber is always kept the high vacuum condition, and only small vacuum chamber depressurize it and gate door open, and we put the device into the large vacuum chamber. After test is done, gate door is open again, and we take it out the tested device. That means total operation cost gonna be very economical. But still, we need to get the government funding from for this second phase small vacuum chamber. As I mentioned before, the large vacuum chamber includes a soil container. Almost 20 metric tons of soil can be get into the vacuum chamber. So with the soil, we already tested the temperature condition from minus 150 Celsius to 150 Celsius using the liquid nitrogen and halogen lamp. And also vacuum condition without soil is achieved 10 power negative 6 millibar, but including soil, 10 negative 4 millibar only we can achieve, because the soil includes a lot of the gases, so it's really hard to get the 10 negative 6 millibar. But from the other national institute working with NASA, and we actually do the survey, and with the soil, 10 negative 4 millibar is more than enough for engineering testing purpose. This slide shows how we can achieve that low temperature condition. For the nitrogen acid, liquid nitrogen, we put connected to the shroud. So shroud actually inside around the large vacuum chamber and the front and back door. So with this the supply system, we can achieve minus 150 Celsius temperature without the problem. But we have to use lots of liquid nitrogen, so that's also one of the big challenges for our research work. First, the soil container gonna be conditioned with a lunar regolith simulant, and then door is open, and we put the soil chamber inside, and using the moving cart, and the moving cart back out of the chamber, and we close the chamber door, and we are ready for the simulate the extreme environmental condition. For dust thermal vacuum chamber DTVC, most important technology is to how to control the soil boiling phenomena, which cause dust emission and contaminate the vacuum chamber, and sometimes break down the pumping system. So it's going to be very severe trouble in the vacuum chamber operating. From our fundamental research, we found that the optimized vacuum speed is correlated to the intrinsic permeability of tested soil, and we found the optimized the vacuum speeds based on experimental and numerical research, and we our final this result is submitted to scientific reports still under review, but hopefully it can be published soon. This slide shows the dust emission phenomenon process. First, start the boiling. It's like water boiling, but we call the soil boiling. And then the dust start emitted. Its dust condition gonna be more severe, and this fluid dust gonna be get into the pumping system and ruin the operating the DTVC. So sometimes people use filter, but filter also plugged, and it's gonna be always change, and maintenance is gonna be really difficult. That's why to remove this soil boiling phenomenon is gonna be very helpful to operate the DTVC. It is possible to put almost 20 metric tons of soil in the large vacuum chamber. To simulate lunar surface condition, we should put the soil which is similar to the lunar soil. We call the regolith simulants. So we actually build up the pilot plants can produce almost 150 kilogram per day. But still, if you want to change or put the fresh 20 tons of regolith simulants, it take almost 4 months like that. But we don't need to change the total fresh regolith simulant for every test, and we think that's it more than enough to produce fresh regolith simulant. Before we build up the large vacuum chamber, we have to check it out. What's the the problems when we operate the large vacuum chamber. That's why we build up the small size vacuum chamber we call the pilot chamber. The total volume is 1 cubic meter, and we put the same soils and shroud and almost a similar system with the large vacuum chamber, and we tested it, and we found the soil boiling phenomenons, and also to achieve the vacuum condition, it takes time. So how we gonna operate it and how gonna cool down the temperature, things like that. And then we from this data we start building large vacuum chamber. So this is very helpful device, and still it's working. So someone who want to do some small scale test or some parts of some device, and we can offer this a small vacuum chamber and quite useful testing equipment. Furthermore, we would like to simulate electric charge the dust condition. So actually in the moon, the light side and the dark side, the electric charge is different. So we would like to this electric charge the dust and dust immigration also. We want to check it up. And why this the electrical charge of dust is important is that this one causes several problems for operating the lunar mission on the surface, because for example, like solar panel is covered by this electric charge, the dust, and the device cannot get the energy, and the mission is failed. Such things sometimes as several this kind of mission failure caused by electric charge, the dust is are reported. So we would like to simulate this electrical charge, the dust in the large vacuum chamber, but still we are ongoing for the fundamental research work. And after we finish this fundamental research, we're going to install this system to the large vacuum chamber, so we can simulate extreme temperature condition and high vacuum condition, and also electric charge dust condition. The second research domain is related to civil engineering works. The real civil engineering works are going to be far away from at this moment. So what we want to do is first, before we construction, we need to make some design and survey for the construction site. So what we want to do is that usually rover includes stellar camera. So using the camera image, and we're going to make the precise map. So that's what we are still working on it. And second one is subsurface investigation for the foundation, how big structure can be constructed on the moon surface. So before that, we need the subsurface investigation. Those things are really fundamental and start point for the construction. In addition, how are we going to get the construction material? Can we just move our normal construction material from Earth to the moon? The transportation cost is going to be pretty high, so it's an inefficient way. So what we are currently working on is that using the lunar soil, and then without the water or without any binder, we can make it solidify and make it brick or block or any kind of construction material. Is going to be helpful to build up the any kind of structure on the moon. So this is still quite fundamental research, and what we are using is the microwave sintering. So microwave is the same as normal domestic microwave, and but different thing is a little bit high energy microwave, and we increase the temperature and without any the binder. So soil start melting a little bit and combine together, so we can make it a kind of solidified material. So we already tested on a small specimen. We succeeded, and we test the mechanical properties things, and it's possibly can be used for the lunar construction. So this microwave sintering, we start from a very small microwave, but at this moment we want to make the really big size blick, so we increase the microwave device a little bit, and we check it out how we're gonna make the solidified material. But one of the big problem is that, depending on direction and location of a microwave generator, there is a hotspot. So it's really hard to make a homogeneous solidified material. And at this, still we are doing the trial error in the laboratory. But from next year, we are going to develop the numerical simulation for a microwave sintering system, and we try to remove this hotspot and based on numerical simulation, and we're gonna modify the device, and hopefully we can make a more big size, real size brick with a microwave sintering method. For this year, we start the numerical simulation for microwave sintering by using the empirical equation. So it's really how to simulate the microwave, how to deliver a microwave to the tested specimen. But without this simulation, based on this empirical equation, material itself inside the thermal transfer is well simulated, but still boundary temperature condition is not quite close to what we measured. That's why next year we need to real theoretical approach how we gonna make the microwave transfer to the tested specimen. And another part is actually we are doing the international collaboration together. Not only we are considering microwave, but also spark plasma sintering also we are considering. And actually, this research is done by the Texas A&M, and we are going to compare the efficiency and the material property things between the microwave sintering and the spark plasma sintering. What are the different they are, and we're gonna provide the sintering method as which one is or any advantage for the sintering method. Next step is the construction site mapping. So this slide shows what we made lower, but this is not a space lower, more like a real field testing purpose. So main focus is that using the stereo camera, we got the three-dimensional the image. We reproduce a three-dimensional image, and from that image, and we would like to make the precise map. The point is that the construction site mapping, we need the location, exact location where it is. That's why there is no GPS on the moon surface. So we have to find the relative location from the lower initial point is, for example, we define the 0, 0 point, and we moving the lower, the relative location can be defined. But only lower location to the image, it's really hard to get the correct location. Sometimes it's a slippery happen, or sometimes tilting, or lower location itself is something problem. So what we are doing is that from the satellite image, we know the some object, and that object gonna be detected and located first, and then from the lower to that object, we can make the location, and whenever the lower moving, the object point is moving. So relative location can be double checked with this system. So we are doing the satellite image and on the surface stereo camera 3D image and combine together, and we can make the precise map. So for the satellite image, there are too many information. So how we gonna check the object is really hard to manually. So we are using AI-based localization. So we can define the several objects using the AI automatic system. So still try to develop it, and the next year possibly more real time, the AI-based localization can be possible. And we would like to check our developed system. So in the close to our laboratory, we make a field test site. So as shown in the slide, and we are doing the 100-meter by 100-meter testing site, and we do the lower test and during the daytime and nighttime. Because nighttime is also what we are focused is that mostly lunar mission is going to the PSR, permanent shadow region. So if we can make a precise map for the PSR, and people and our technology can be applied to the other missions. So, for example, if rover get into the PSR, they cannot see the inside of that dark side. So it's impossible to get into, rover drive into that dark side. So if we have this like a technology for mapping in the dark side, it's gonna be really helpful for international collaboration. So that's why we do the tested it, and it works pretty well. Enhance the image like a technology, and we combined with our 3D mapping system. It's really working well. And also AI system also we don't have the satellite image yet, so we use a drone image, and the drone image from the drone image, and we check it up the object, and the AI system automatically found the object without any problem. Finally, subsurface investigation. We make the drilling device, which is based on the icebreaker from the Honeybee Robotics in States, and we are build up our own drilling device and check it off in the Antarctica, South Pole, in the extreme temperature, and also mostly nowadays the lunar mission is I said before that heading to PSR to detect the ice in the moon. So we target for the ice drilling, and we would like to find some ice material mechanical property based on drilling systems information. So I'm going to present in next slide. So after the Antarctica performance test, we test our drilling device in the vacuum chamber, and we try to penetrate the gypsum and the legolas similar to mixture. So as shown in the slide, right after the vacuum, 5 millibar is a little low vacuum condition, not a high vacuum condition, but still we can check it off the performance test for our drilling device. So right after the vacuum condition is achieved and we start drill, you can see a lot of dust is around the inside the chamber, because this is quite similar to the dust emission what I explained before, because gypsum and legolas similar mixture has a very high strength. And then when we depressurize it, but still inside that the mixture specimen is the pressure is still remain. That's why when we start drill, it makes its airflow the channel. So airflow is coming inside the specimen, is coming out of the specimen, and then this causes this kind of dust emission severely. But we stop drilling and 24 hours stay in the 5 millibar and then test it up, no problem. So which means inside the specimen and outside the chamber pressure is equalized, so no more dust emission happens. So, and what we found is quite the verified again the dust emission problem well, and also our drilling device is working in the low vacuum condition without any problem. And the other one is that I said before that to find some mechanical property, we use the same like gypsum and legolas similar to mixture. During the penetration, we measure the penetration rate and also reaction force and torque from testing the drilling device. And then specific energy is well defined, and using this drilling information, and we make a correlationship with the strength of the material and specific energy, and it's showing that almost linear, and the agreement is pretty good depending on strength and specific energy. And so specific energy increase and strength also, material strength also increases. So from this research work, we can conclude that the drilling device, if we measure the drilling information during the subsurface investigation, we can define the some kind of material differences, or sometimes we can detect ice in the lunar under the ground. I would like to close my presentation with a KICT vision for lunar construction video. Again, thanks for having me a chance to present our research work.
The closest celestial body from the Earth, Earth's only satellite, the Moon. The Moon now becomes a station for humans to travel into what was considered outside human limitation, space. The beginning of a new future, lunar construction. A lunar orbiter launched from Earth enters the lunar orbit. It initiates remote reconnaissance as it explores the lunar surface to identify sites for construction. It collects and analyzes geographical, resource, and environmental information, identifying the most optimal location for construction. A robot for more detailed reconnaissance arrives at the construction site. The first task of the robot is to go over the ground and with its camera collect detailed geographical information. And with its exploration drill, collect geological information. It also confirms the location of a safe lava cave for human habitation. Another robot conducts construction material testing with the Moon's resources. The robot's thorough and comprehensive reconnaissance is an imperative step of evaluating and verifying technology before actual lunar construction. Based on this verified technology, robots with construction equipment make their landing. The first step is to set up a power station for energy supply. And next is the construction of a landing pad to prevent the occurrence of dust, which could be deadly for astronauts. And the construction of a blast wall for protection from meteorites. This is the lava cave, confirmed in Phase 2. It is the optimal place to keep safe from the strong radiation and meteorites flying around space. And it is where a habitation zone will be built for humans. Finally, the lunar station construction phase. Astronauts arrive and safely enter the lava cave where humans will habitate. Roads, an advanced base, and power station for both habitation and development will be constructed. Overcoming severe environmental conditions, this will be the completion of the city of the future humans have dreamt of. Based on the rich energy resource of the Moon, We are preparing to travel further into space. The endless challenge for a bigger world. The research for the future continues on.
Thank you for your presentation. Another point. Can you turn on the microphone?
Yeah. Okay. Yes, it's a pleasure to be with you from another continent.
Yeah.
And so I would like to show you.
Could you share the PPT material?
Presentation. Yeah, so do you see my presentation? So yes, I would like to make an overview of some moon Mars missions, the science, the technology, and also simulation that we have been conducting. And this helps also to inform how we are going to build the next steps in a phased approach up to the stage where we use resources and also we will construct moon base or even a moon village. So here I want to thank Professor Taisikli and also Hank Rogers for their collaboration, and also a cast of ILRIG International Lunar Exploration Working Group and Human Mars Group, where we have a number of researchers joining us with also a large number of professionals and even space ladies that I've indicated in pink or red colors here. So clearly, the moon is an important destination for science, but also because it was a part of Earth and because it will be the 8th continent for our civilization to settle. We can learn about the early Earth moon systems, about also rocky planets. It also holds a record of solar system impact, and it has a very special environment. So we have been there actually in Europe. Was leading the first mission of this millennium to the moon called Smart One with a team of engineers. You can see in blue suits, also with the operation team and some of the science teams with various instruments that were built on our Smart One probe that we built and prepared in only a 3 years time scale, and a small spacecraft of 1 cubic meter, 40 meter solar panels with new technologies on board. So indeed, we have some special technologies there that could be reused in futures. Technologies of communication with laser communication or microwave. Also technologies for spacecraft with very sensitive solar panels and onboard computers, intelligent batteries. Also technologies of a very miniaturized instrument, a micro camera, 250 gram, an X-ray spectrometer to measure elemental composition, or infrared spectrometer to measure minerals on the moon. And we also add some software and some new algorithm for onboard autonomy. So we used a solar electric propulsion engine that allows to spend 5 times less propulsion ingredients. So with only 60 liters of fuel, we went to the moon from Earth orbit. So that was after 3 months in the radiation belt. We took some picture of Europe, and then we had a long trajectory that lasts 1.5 years. But we use this trajectory to decommission some of the instruments and look at our beautiful planet. Actually, in some of the pictures, you can even see Korea. When we were at 150,000 kilometers from the Earth. And arrive at the moon, then we delivered some of the science, in particular comparative planetology, looking at processes that shape the planet, like tectonics, impact craters, volcanism, polar regions, special processes with the cold and the volatile, and also we conducted our own impact experiment with the spacecraft bouncing on the surface, landing at hard speed, and we could observe this flash and ejecta from a telescope. We surveyed polar regions, so both poles, but in particular the South Pole at high resolution, where we looked at areas of permanent shadow, and also as we stayed more than 1 year and a half in a science orbit, we could monitor seasonal effect of light. Here are places that we could explore, so impact, and in particular, close to the South Pole, on the rim of Shackleton, we could discover an area which is a peak of light. It's called Smart 1 peak of light. It's on the bridge towards the Gerlach crater, and where you have almost permanent sunlight even during the winter. So that's where we could in place some of the first robotic village and man outpost before we expand on the overall surface of the moon. Eventually, at the end, we landed, and we had, in fact, a bouncing 2 kilometers per second on surface, and we could detect, in fact, 10 years later, this bouncing stripe and some of the Egeta streams. So after Smart 1, and at Smart 1, we were alone around the moon, but we collaborated with a number of countries over the world. We collaborated with US scientists, with Japanese, Chinese, Indian, Korean, Ukrainian, Russian. And based on this collaboration, we have fostered a community which was started with the International Lunar Exploration Working Group, where we exchanged data. We also exchanged the possibility to fly instruments on other spacecraft, like ESA flew a free experiment on board the Chandrayaan-1 spacecraft. And we also collaborated with the Chinese in order to, for instance, support their telecommunication and their control and the data rate on all their Chang'e missions, starting with Chang'e 1, where I was negotiating with them an agreement to give our organization access to support the Chang'e program. So more than 20 years ago, we had created the International Lunar Exploration Working Group, and Professor basically is our vice president at the moment. And so we started with Professor Curien, Professor Geis, and we had a number of presidents there. And we organize every 1-2 years a large community event, international conference on exploration and utilization of the moon. And already in 1998, we set a phased approach for exploration, a roadmap toward the moon village, starting with a precursor mission in orbit and on the surface to survey, to prospect, and then a phase with the deployment of robotic village with small robots, landers, but later larger heavy-duty robots that can place modules for habitat, food production, energy production, or even manufacturing or robotic constructions of a manned system. And then we are looking towards the moon village phase, where we'll have a permanent habitation with humans and robots. And this could be happening from 2030. So clearly a number of science questions we want to address, as the moon is a great continent to learn about the condition for the formation of planets, how the solar system works, looking at comparing the processes of planetology that I've described before. But also it can be interesting to understand the condition for life and ingredient of life, as now in the polar craters we have found some volatiles that contain not only water ice but also organics that could trace some primitive bodies that deliver some of these organics to planets, and we could study those layers on the moon. And also you can validate the detection of extreme organics and life in a polar region. Now, for sure, in the future, we can also test how the moon is habitable for life or for humans. And we can perform life science experiments, in place ecosystems and mini biospheres on the moon as a first step to move our civilization from one planet to 2 planets and then to other places in the solar system. Even we could search for early Earth samples in the moon that were deposited there 4 billion years ago, and from an epoch when life was emerging on Earth. And also on the moon, because there's no atmosphere, you can deploy telescope or radio telescopes to do science from the moon, to observe the Earth, the solar system, the galaxy, or even the cosmology, or even search for extraterrestrial intelligence. So as you've seen, the vision that we have set with the ILUIC roadmap has been happening, as now we are really in full in the phase of the surface robotic village, where already in 2013 we had Chang'e 3 lander and rover. 2019 we had Chang'e 4. We had now sample return, and we'll have a series of commercial missions and also US commercial payload and a number of international missions, including carry Pathfinder, Korea Pathfinder orbiter, but also some landers from Russia, from the US, from Japan, possibly also from Korea, and from ESA. So that the robotic village will be really in full speed in the next years. But in parallel, we have also a number of expeditions that will include humans. In particular, ESA is collaborating with NASA for the Artemis program, where we produce a service module that can bring the overall Orion capsule around the moon. So we'll fly with that in automatic mode in 2021. And in 2023, there will be 4 astronauts around the moon. And 2024, we'll have even 2 of them that will go to the surface. That's the current plan. So that's a view of the Chang'e 3 U2 rover, and we had also a similar U2-2 in Chang'e 4. And that's a platform of Chang'e 3, very similar to the spare one, which was launched to the far side of the moon, Chang'e 4. And this same platform was also adapted for the latest mission, Chang'e 5, to hold as well an ascent vehicle that and devices to fetch samples on the surface, in the subsurface, and then put them in an ascent rocket that rendezvous in orbit as a bird first around the moon, and then transfer the samples to return a capsule that was injected with a great precision to be recovered in Mongolia just a few days ago. Big success. So in our side also, with the International Lunar Exploration Working Group and the support of some agencies such as ESA-ESTEC, but also NASA, we have worked on some concept of instrument we can put on small landers. But we built a Google Lunar Express lander with one of the team, and we tested some instrument and some robotic system on board. So we put also telescopes, as we will have also telescope on the surface of the moon. Actually, there was one telescope on Chang'e 3, observing also the Earth's environment and also the stars variability. So these telescopes and instruments are teleoperated from a little moon-based module, which is where we control some of these experiments. And we also deployed from this ExoGeoLab lander some small rovers that can work together, and we tested some concept of cooperative robotics, where some rovers can be specialized in handling samples of material or even some construction tasks, and others are specialized for doing analysis of samples or prospection. So here you see we even put our lander on the surface of the moon with an astronaut. And in fact, this was obtained during a simulation that we performed in a volcanic site in Germany, so close to the European Astronaut Center. This is a result of a lava fountain. So we have heard about the lava fountain on the moon. We have also some on the Earth, some ashes and pyroclastic explosion that deposited, for instance, 25 meters of layers in only a few weeks, some 10,000 years ago. So we went there with with our lander, with astronaut, and with rover to demonstrate the operation of such a cooperative family of robotic systems like we would be on the moon. We have also conducted with in an effort led by the German Aerospace Agency, DLR, a campaign called ROBEX, where we use some big lander that was designed actually for a previous project of an ESA, a lunar polar lander, but also two intelligent rovers that can go and deploy experiments that were carried by the lander. They can also participate to some installation and some construction tasks. They can autonomously perform exploration and a series of tasks, and but they can also be teleoperated from Earth. So this we had a campaign at Etna, so that's also a very good analog for the moon. In terms here, that's an area where you had also some of this pyroclastic lava fountain deposit, and very similar to what you would find on the moon. Actually, we are currently preparing a large campaign again for next year, and it's called now Arches. It's led by the German Aerospace Agency, and in this campaign, we are going to deploy with this rovers a series of modules that have different functions: sample box, line repeater, power box, box with instrument like a laser-induced breakdown spectroscopy to measure the composition of rocks, a box for communication and navigation. Even we'll have a box that will contain ComNav, but in addition, radio antenna to study the low-frequency radio emission from the sun, from Jupiter, and also from the galaxy, like we will want to do on the far side of the moon. And so, and actually the location of this campaign from 14 to end of June 2021, we will want to organize a demo for the community at large, and we would like to invite you. We will have a workshop for VIPs and a demo where we expect that you could talk and also present some of your own research and development. So indeed, we have a number of revolution in robotics, robotics of the rovers, robotics of androids, and teleoperation. Now, this is leading to the next phase of a sustainable presence with human on the moon, where we use robotic system to deploy a large infrastructure. We will deploy some modules, inflatable, but as well we will use rovers, and that will be able to 3D print some of the protection for this habitation, or for some laboratories, or even factories and manufacturing modules. So indeed, we have a number of efforts to address challenges for this moon village implementation. So landing there with soft landing safely, and for other human vehicles, but also large cargo vehicles, the communication with Earth, operations of the facilities, survival of astronauts and of equipment, also mobility in this on the surface, and having a partnership between humans and robots, and as well making use of the local resources, some mineral or volatiles, water, ice, and power that you can find there. But also the new challenge is to involve newcomers, so new space, but also non-space companies and academia and research institutions, and explorers, innovators, and entrepreneurs into this endeavor. So at the European Space Agency, we are looking at for human exploration at destination like low Earth orbit, where we are part of the International Space Station. We are also looking at what will be happening at low Earth orbit space station after the ISS. And then the next destination is the moon, in orbit around the moon with the Artemis program, but also on the surface of the moon with robotic collaboration with Cosmos on the landers, but also our own lander, and also participating to the effort to have a human on the moon this decade. And in parallel, now we have effort also on Mars Mars robotic mission, mostly at the moment, but we are also thinking at a future Mars human mission. So we made some joint studies with NASA and other agencies. How would be the implement of some of this first outpost module? And so here, for instance, an habitat module, and you could have also a pressurized vehicle with airlock, and that will allow sorties with astronaut to explore, to prospect. And we looked at yes, some various architecture for this operation of this moon village. But now there are clearly new progress in the areas of rocket, large rocket, but also systems, and we are now conducting a number of studies all over the world, different agencies and also institutions looking at what the moon village various places could look like. So from the point of view of the International Lunar Exploration Working Group, we started 10 years ago a program called Your Moon Mars, which is also to gain some practical experience with instruments, with technologies, also with simulation in Moon Mars bases, where we take some of our young professionals, we lock them for a few weeks in a moon base, and they can perform laboratory research, field research for geology and astrobiology. They can demonstrate some instruments like cameras, spectrometers, rovers, drones, techniques for navigation, for prospection, drilling, sampling, but also we optimize what should be the habitat technologies for in terms of structure, layout, but also the subsystem of power, communication, gray water, greenhouse, food production, and a laboratory, which is always a part of this simulation as we are looking at a research-driven first phase of human exploration on the surface of the moon. And also there we are studying human aspect, performance of the crew, and how they use their time, and also how they prepare their extracurricular activities, and also the whole medical follow-up of the astronaut. So we use this opportunity as well as a platform to train young researchers, advanced researchers together to transfer knowledge, and also to outreach to the public or to the youth or to the universities what they are learning. So for instance, already from 2009, we have had a campaign every year where we have 6 crews with different tasks, commander, executive officers, scientists, engineers, habitat engineers, medical aspect, also humanities. But here, for instance, we had a set of experiments in collaboration with NASA Ames Research Center, X-ray experiment similar to the one sent to Mars on Curiosity, Raman spectrometer, microscopy, and also we had some equipment for extravehicular activity with a ground penetrating radar delivered by the Jet Propulsion Laboratory, and we had also some tests of drilling with the humans and taking some samples in depth that were later analyzed. So also with the EDUIC and the support of ESTEC, we created a mini moon base where we lock the astronaut for a few hours during the day, and there they can test the protocol for communication with us, protocol for sample analysis. Here you can see, or even they have a 3D printer where they can manufacture some object or accessories that they need for their operation. And there is also a back room, dark room for doing some additional work and rest. So we also tested more recently one special biology laboratory where you can do sterilized sample analysis, but also you can have life science experiment, or also do some plant growth studies. So in particular, the moon has a great regolith that can be used for construction, for extraction of materials, minerals, metals, volatiles, but also we have made experiments where we could grow plants out of moon soil, even if this moon soil is very poor. We developed some techniques where you can, even without fertilizer, extract some of the key ingredients for plants. And we also looked at some techniques where you could do that in an early phase already with robots and with some robotic gardener. So now from the human side, we have performed a number of isolation campaigns. This is in a Moon-Mars base called Lunar in Poland, where you had a 2 weeks simulation, like it would be the first campaign to the moon. And here such a crew of young professionals before their expedition of 2 weeks, you see all smiling and very happy during the course of this expedition because they had a great research to perform, but also we fed them with plants grown locally and they could take off with aquaponics. So Urban Mars has also organized some campaign in sites that look like the moon. This is, for instance, our Mars. This is, for instance, Iceland, where we had a little expedition 2018 and also 2019 and this year. And we also prospected some lava tubes from the possibility next year to in place a subsurface habitat and laboratory in some of these lava tubes that could be deployed by a crew of 4 astronauts. So really for deploying a first outpost with a surface station, but also an habitat in the lava tube that protects from radiation, from meteorites, and which has also a good temperature regime. So last year, in the frame of ESA Lab, which is a group, federation of laboratories in Europe that are working with ESA, and we selected the first pilot project, which was to build a moon base, moon habitat under ice. And so we had a team of 20 universities, each providing various subsystems for power, for life support, for communication, and for instance, the International Lunar Exploration Working Group and the Free University of Amsterdam provided science experiment and investigation, as well as the lander, or lander that was put on the top of the glacier. But here you can see some of the robots that were developed that could be used for construction, and one of the habitat that was designed, but also a plant growth experiment that was conducted with a robot to operate, but also to determine with artificial intelligence when was the best time to collect the plants for consumption. So more recently, also in collaboration with the International Moon Base Alliance, and actually Professor Taisikli is one of the directors of the board, together with me and with Hank Rogers, with the founder, we are now exploiting this facility called ICES on the Mauna Loa volcano to perform a simulation of what will be life on the moon base for 2 weeks. So this is a view of this moon base. You see very moon-like with a lava similar to what you would get on the moon, and with sustainable autonomous solar power and operation that are conducted by the astronauts. So I was there in 2018 for a technology precursor experiment with Hank Rogers, the founder, and a few other analog astronauts, where we brought some instrument for surveying, like a drone, extravehicular equipment, but also some instrument to analyze samples that we collected there. But after that, in 2019, we started a series of a campaign called Euromoon Mars, International Moon Base Alliance ICES, EMIS in short. And here also we installed a ground control station. And here, this time I was comfortably in this control station as a flight director, and my students were performing in hard conditions their extravehicular activities. Here they were repairing an antenna. Here 2 of my geology students are collecting samples that they use for their master research, analyzing the alteration of this basalt, also when going into lava tube to look at some microbial mineralization. But also they learn how to to cook space food. So you see, and so there are some recipe, not as good as Korean cuisine, I have to say, but still to the delight of the astronomers. So we had a French cook. He could cook some French dish, just starting with powder food, and they have also had a great human experience, learning with people from different countries, different backgrounds, to live together like they would be on the moon. So in the next step, there are a number of activities all over the world to develop some moon simulation facilities that integrate also the properties of the soil. So at ESA, we have a Lunar, now which is built. This was the first concept. Now we will have also a big building with a number of laboratories, also an habitation module called FlexHub, and also various set of guest facilities. And but clearly a very important one is the dirty thermo vacuum chamber, which was built in KCT, and the great inspiration of Professor Taisik. And I was very fortunate to be involved in the discussion, but also in the inauguration of these facilities. And I'm really looking forward to return there and to make use of it with some of our collaborators. So for instance, this is a view of the inaugural day where, okay, we were just rejoicing of this event and great achievement. And also we did some work with the media to advertise to the public the importance of this development. So clearly, I've had a great experience of every time I went to Korea. I started at the International Astrophysical Congress in Daejeon. Actually, that's where I met Elon Musk, and also a number of other key people, ambassador for space. And then I had the pleasure to come for a Moon Village workshop that we co-organized with Professor Taisik, and also for Korea Space Forum. And I'm looking forward to the next steps with the Korea Lunar Pathfinder and also the lander. And I had also the pleasure to come there also with my daughter, Victoria. And also we could share also the great friendship and the culture of Korea and the food. And clearly we want all of this as well with us on the moon. So as a summary, yes, in order to prepare Moon-Mars Village on Earth, there are a number of activities that we are engaged in where we can make a contribution in various countries or in collaboration on the landers, rovers, telerobotics, instrument, field tests in analog, in-situ resource utilization techniques, also life science, even the robotic phase, and the use of the dirty thermovacuum facilities, like the one at KICT. But also we are learning from simulation that we perform in human habitat, laboratories, infrastructures, on the hardware, but also on the operation, on the human aspect of developing these activities, also in partnership with robots. And so also a very important factor is how we use some of this effort as well to inspire, to train the young people, and even to engage other disciplines, designers, architects, artists, in addition to scientists, engineers, and industry, because this village will be, the Moon Village is an initiative that has to benefit everybody, and we want that also the different stakeholders for the future on Earth and those that will go to the moon be engaged already from now. So I want really to thank you for inviting me to talk to this workshop, and I really appreciate the progress and also how you are driving some of the effort in Korea, but also with a large international cooperation. And I'm really looking forward to come and visit you, also to greet you when you come to Europe. Thank you very much for your attention.
Thank you so much, Bernard. And thank you so much, Professor Kyung-Ja Kim, and also Dr. Jang-Geun Lee, and then Dr. Bernard Foin. we are very lucky. I have my good friend from California. Right now it's 12:30 o'clock, and then Madhu Thangavelu, professor of University of Southern California, and we are very lucky to have him here. Welcome, Madhu.
Thank you all. Can you hear me?
Yeah.
It's good. Okay, good. I thoroughly enjoyed Bernard's slides. We are getting more and more used to performing every other day now. We had several meetings in the past, and it's a pleasure to see you, Taisik, after so many years. I've once in a while, in fact, yesterday too, somebody screened the vacuum chamber that you have nicely built, and we are all looking. All of us want to use it for one purpose or the other, Taisik. Now, I would like to tell you about the things that are happening in the Southland. A few miles down the road here is where SpaceX have their headquarters. So many of my students finished school, and many years ago, they used to all want to go to NASA. But in the last 5 or 6 years, all my reference letters have been to SpaceX and Blue Origin. So this should tell you something about what is happening in the new space arena. My students, either at the graduate or the postgraduate level, they are very interested in doing things that happen fast. They don't mind working 24 hours a day, but they want to realize their visions very quickly. As you know, Elon is also a very hardworking person. He drives his company hard, and we expect to see magical things come out of that small company in the coming years. To be more specific, in the coming few days, you will see the test flight of the next generation of Starship. It is, as you know, Elon has pushed our industry to move away from expendable launch vehicles to reusable launch vehicles. And I'm delighted to see that the world's space agencies are all looking towards reusability, sustainability, and self-sustainable activities in the space frontier. And all this is good, not only for space activity, but also for the things we do on planet Earth, because many of them will tell you they do these things not to go out into space, but to do things that are good for planet Earth. I am reminded of this very well-known visionary and engineer by the name of Kraft Erike. He used to live here in San Diego. I met the gentleman many years ago. Very inspiring person. When he was asked about why we do space, he said, it is not about space activities, is not about working and doing things in space. It is about providing very high quality jobs for people on planet Earth. And this is true because when you look at the various agencies of the world today, they all come across as some of the finest places for people to work. And so with that, I would like to share some slides, if I may, that I presented yesterday at the American Institute of Aeronautics and Astronautics here in Southern California. Now, Taisik, if you can lead me to the slide, events here. Let me see if you can share the slides. Am I on there?
Yeah.
Oh, great. Okay. Let me go full screen here. Good. So now, some years ago, actually some 20 years ago, we wrote a book about the moon. And in it, we stressed that the moon is the closest place for us to experience and simulate more ambitious work in outer space. And that is exactly what this outgoing administration has put into plan and started rolling in what they call the space policy documents 1 through 6. In fact, the last number 6 space policy document just came out a few days ago. And the national space policy document was framed also 3 days ago. So I want all of you to look at what this outgoing administration has laid down as the principles for the incoming administration. In my opinion, they've done a fantastic job. So going back to our book, it came out in 1999, and many of things discussed what we could do on the planet, on moon, that we called Planet Moon. Bernard also says this sometimes. He says it is the 8th continent of our world, and it's a very special continent, because when I come out in the morning and I look around, I cannot see any other continent. I cannot see Africa or Australia or South America, but every night I can look up and see the 8th continent going up in the sky. In fact, tonight I was out with the telescope looking at the conjunction of Jupiter and Saturn that I wish all of you to see. And we saw a beautiful quarter moon up in the sky. And I put some images out for Bernard and others to see on Facebook, and the Taisik too. Okay, with that, let me proceed with what we do. So the University of Southern California has long had an interest in aerospace activities. Neil Armstrong was a graduate student at our department when he was called to fly the moon mission. And when he came to the dean and told him that he had a mission to go, the dean asked him what it was. At that time, he was a test pilot at the Edwards Air Force Base. So Mr. Armstrong came into the dean's office and he said, I've been tasked to be the commander of a flight to the moon. And so the dean, as all academics, including Taisik, might say, well, if that is the case, you must submit a report when you come back, and that will be your thesis. End of story. So anyhow, we have this program, and we do distance education networking all over the world. So you must take a look at the USC Astronautical Engineering program. Within it, I teach a course that is a combination of architectural concept synthesis and some engineering. My background are in engineering and architecture. In fact, I had a good group of students from the National University in South Korea visit me at my home.
Excuse me, Madhu.
Yes.
Some of the discussion people should leave. So maybe wrap up 3 minutes.
Yes, it's going up fast.
We can talk.
Okay.
Whatever
good.
you like.
Okay, good. I'm going fast. So
okay.
Please look at this site to see what we do. It's all about imagination and creativity. Now, in terms of construction, which is what you're thinking about, we have been doing some very interesting studies, not only for the moon, but from vehicles for Mars and for interplanetary missions as well. And this is our finals exam. We have wonderful friends who come. Buzz Aldrin is a close friend of ours and visits all our finals presentation. And you'll see my class looks like this. This is my architecture class where I do creative imagination and thinking about the next future for stuff happening on planet Earth. So we look at things like what happens in the year 2050, implications for future city developments, in which South Korea is very important. And we look at things dealing with projects that really look outward and future to the next 50 years. That's Buzz Aldrin signing a book. And what I do in the class is create ideas for people to think about. And we move from idea to idea. And these are all construction projects that we hope to do in the coming term. In regard to the International Space Station, we hope to build large modules using the Starship to enhance commerce in space. To go to the moon, we want to do resorts and hotels orbiting the moon. We want to fly large landers, and we want to rove on the moon using large rovers, much bigger than what NASA is planning. We will use robots, like the one you're seeing here called the Centaur, or the Robonaut. And this comes to our topic of interest for TISIC. Some years ago, NASA awarded us some amount of grants to think about 3D printing on the moon. In fact, the first grant was in 2012. In it, we decided that we would use regolith blended with some perhaps sulfur or even polymers now to build structures on the moon. And here you see the depiction of what we could do using a particular process of 3D printing called contour crafting. Please make a note on it and check it out. The idea is to build structures on the moon, just like we would on planet Earth, using a gantry system with a variety of materials that are available to us with extremely specialized technologies, including end effectors and nozzles on gantry machines. Our idea is to build a lunar landing pad first using this particular technology. Why would we do all this? Is it only for science and technologists, or to make a self-sustaining possibility? We want to generate revenue that you can feed back into the cost model so that we can have a profitable business. One idea is to have a railroad on the moon that would take people and show them what the moon is like on a ride from pole to pole. This is what we would do if you had a beautiful set of railroads on the moon to carry people on their holidays. This is what it would look like. And the second thing we would like to build is a planetary defense system on the moon. When you put structures on the moon, you're going to have to protect them from micrometeorites and meteorites because the moon does not have an atmosphere. So what we think is we could have high energy, directed energy lasers that can just pop out these little pellets that come at you in case you need to protect your exposed assets. This is what a large-scale development on the moon might look like. Not small little laboratories to do specific experiments, but very large-scale operations containing activities for retired peoples, for entertainment, for United Nations to have summits where they can look at planet Earth and decide the future of all the people of the world. This is what an Olympic stadium might look like. And this is what we think we could do to preserve libraries and knowledge on the moon by setting them down. How are we doing on time, Taisik? How are we on time, Taisik? Is good?
Yeah, it's almost done. So
okay, good.
Finish it.
Okay. Now, I want to mention a little thing about space philosophy that we should all impress deep in our minds. In the 1960s, there was a polymath by the name of Buckminster Fuller. And he grappled the same questions that we grapple now. How can we have a sustainable civilization that takes care of people, that more importantly takes care of planet Earth and not pollute the planet, and how to be efficient in the way we do our work and the way we conduct business. And he suggested that we become frugal and become efficient in energy use, in material use, and think beyond science for sustainable futures. These are the young people, some very young, who have got new ideas about our future. Elon Musk, who lives here, thinks our first primary important job is to settle the other planets, because we have to make our species survivable if things go badly wrong on planet Earth. Jeff Bezos, who lives right not too far from here, also thinks that the most important thing that we need to do is make Earth, preserve Earth, the quality of life, improve the quality of life, and make Earth, Mother Earth, beautiful. John Marburger, who was George Bush Sr.'s science advisor, was the Dean of Arts and Letters at USC before he took that job. And in his address to the Goddard Memorial Lecture, he said that one idea is to bring all the solar system's energies to bear on planet Earth. He called it bring the solar system into the Earth's economic sphere of influence. It's an interesting idea. Joseph Campbell talked about the return of the hero. For those who don't know about Joseph Campbell, he wrote a lot about mythologies and how storytelling is important, how narrative is important. In fact, all of us growing up listened to stories from our grandpa and your grandma and your dad and your mom. We read stories. And so storytelling is very important, whether we are in the sciences, in the technologies, or other kinds of activities. Joseph Campbell was the mentor for George Lucas, who produced the Star Wars series of movies. And George Lucas is an alum of USC, and he is building his museum of the narrative arts. It's not called space, it's not called rockets, it's called the Museum of the Narrative Arts across from our campus. And I would like you all to visit it because it's building up to be the most efficient building on the planet.
Madhu, thank you so much for your early in the morning, 1:30 in the morning.
These are all of the ideas here. I want to bring up these people, and remember that everything we do, we should keep in mind that planet Earth is the ultimate receiver of these important things.
Okay, thank you. Dr. Jang-Geun Lee, I know you should leave, so could you comment? What did you learn, and then what do you want to talk?
Yeah, I will leave you with the slide, Taisik.
Yeah, thank you, Madhu.
Thanks for having me. And actually, we ready for the testing the logic. Can you hear me now? By the way,
yes,
we can all hear you.
All right. So we actually are ready for the simulate the lunar surface environment. But the point is, the Korea government is not ready for the for lander or rover testing. So if you have any kind of international surface mission, we would like to have the some international collaboration for the testing equipment. For example, we can just provide our facility with only like some electric charging. I mean, just only the direct cost only. So it's a pretty good chance for you guys, to test your equipment in Korea if you have any kind of obstacle to export your device. So we can help you guys to verify and testing your equipment. Anyway, so our DTVC is really, really ready for the real test. That's what I want to say.
Okay, Jang-geun, thank you so much. I know that you are Christmas vacation right now, but you gave the time for us, so thank you so much.
You're welcome. So thank you very much.
Yeah, and Dr. Kyung-ja Kim, she has been sick, and then temperature is high, but I don't think it's corona. But thank you so much for your participating in this seminar.
Thank you so much for me.
It was a great talk.
And I think now we should really focus on future collaboration. When we really look at the slide of Bernard Boeing, I think we should go over what areas we can collaborate. And Korea is very interesting areas. I actually went to Iceland, but I know there's a base already. German made a base for the cold areas. But I think Korea is very interesting place. We have a very large lava tube in Jeju Island, and there are some research can be done in Korea with respect to like terrestrial analog, especially for Moon and Mars. I hope we can have some future collaboration, very practical way. And I will have one student just accepted for me, and at University of Science Technology. Her dream is to prepare for terrestrial farming, especially farming on the Mars. So students coming not this way. So I think we urgently needed to do some collaboration, because ESA has much advanced, way of research and technology available for future collaboration. So that's my, impression today. And actually, today the talk and everything was so, precious and very advanced talk actually. And I think not many students or some people are connected. We actually have ISLU group, and with a PhD level of scientists, about almost 20 in different national institutes. We should really combine this kind of research group, Lunar ISLU group, together with this kind of, Professor Tashik's, this kind of seminar event. So let us continue our, event like this. And I'm ready to promote this kind of science with other researchers together. Thank you so much for your talk today.
By the way, I'm proud of Kyung-ja, because her instrument will fly to the moon in 2022. What is your instrument name?
Yeah, this gamma-ray spectrometer. So we have 6 instruments, and one is a shadow cam that is made by NASA. ASU, the Mark Robinson is the PI. And this month we are submitting all the payload to CARI, and next 1 year we prepare for final, checking, right? And then it will be launched by, supposed to be August in 2022. And promotional video actually came. I mean, I have seen, but I don't think it is released yet. And I'm sure when you see that, and you can know that how Korea is eager to go to the moon and Mars, and future technology will support future space mission Korea together with the other international partners. Thank you.
Thank you so much, Kyungja.
I'm in close contact with Mark Robinson about that payload. It's wonderful to know that it's progressing very well. Thank you very much.
By the way, Madhu, you missed my presentation, and I gave the first picture was that our picture on the International Space Station.
Okay.
In you.
Thank you. Thank you.
Thank you so much, Bernard. Early in the morning, 7 o'clock, 7:30, you join us, and can you give this some comment or the advice?
Yes, I was very pleased to hear the different presentations, yours, Tracy, and from KICT and from Kim. And clearly, we are eager to continue this collaboration that we have started. So now, still virtually, actually, I have now a student in Korea, and he's doing his internship, and but he's very much into quarantine. Now, I think this series of workshop seminars that you have started, Taisik, it will be good to continue. As well, no, I still remember the Moon Village workshop where you also pulled a number of stakeholders. So it will be great to find an opportunity to have such a workshop, possibly starting virtual, but I hope after the second half of next year to do something in presence. So we were looking last year. I mean, I don't know if IAU is still happening next year in Korea, but in any case, I would like very much that we could have a field campaign, Korea Moon Mars. You know, here we have Euro Moon Mars, but we could do Korea Moon Mars, where we could come with some of our experiments, and we will test them in Iceland in May, June, also in Etna in June. But we could take some of this experiment, some rovers and instruments, and be part of a Korea Moon Mars campaign in some of the sites that you know well. And it could be an opportunity to do both a workshop, but also hands-on work, also targeted towards the preparation of space missions. So I'm looking forward to that maybe at the end of next year to try to schedule that when we are all vaccinated and eager to travel and come to Korea again. Now also we are preparing a number of events in Europe, in the world. So for instance, with the International Astronomical Congress, we will have a big conference in Dubai, still planned at the end of October. And we have the European Planetary Science Congress in Helsinki, in Finland, where also we are planning to do some general workshops where we can present to the broad planetary community, but also some hands-on field work. So hopefully from that time, we could have an opportunity to meet you as well in Europe.
Sure. Madhu, I cannot give you the one.
Yeah, Bernard, I have one thing I want to inform you. You know, there's Europlanet 2024. Do you know about that? The KIGAM became, there was a call related to planetary collaboration. So KIGAM became beneficiary for 4 years. So we are proposing collaboration at the moment. So I hope this activity can be well informed and then really work together for field site studies as well as laboratory work and together.
Okay.
I will
yes,
say more details.
We have this platform of access to facilities, and then there is a bit of funding from Europlanet to help some of the trip and stay logistic to visit facilities. So that would be also a good enabler for something concrete.
I think that I missed the last conclusion of the Madhu, but I cannot give the 1 hour. You know, you is 1:30.
Yeah, you know, the concluding thoughts.
Only minutes, please.
Yeah, the concluding thoughts are there is a lot of interest right now, as Professor Kim said, in lava tubes. And they are a very straightforward way to establish permanent habitats on extraterrestrial surfaces. To all of you in the science and technology industry, I've been looking at this for many years. I think we must deeply impress on our communities why we do what we do. And it is not only about science and technology. Much of it has to do with inspiration coming from deep within the heart. Some of the things humans do are not logical at all. I was reading G.K. Chesterton the other day, and he says, there is a road from the eye to the heart that does not go through the intellect. It is true. If you look at how policy is conducted in the world, you can be the most logician in the world, but it doesn't bring you the happiness and the enjoyment that you get from doing fantastic things. So think about it.
Thank you so much, speakers and presenters.
For the why, yes.
Yeah, by the way, any participant want to say anything, 남태 or 경찬, 병회, 나리, 박진호 교수, 장석일, 와이슬리,
maybe could we put all our camera so that we can
yeah. Can you turn on the camera, please?
Ah, yeah. Yes.
Okay. Oh, Mr. Chang, you had your background.
Yes, yes.
Okay.
But Madhu, the why maybe, one point, Madhu, the why maybe is not logical, but to do it, how you need logic and engineers.
Oh, absolutely. Oh, I fully agree. And they know the inspiration.
Anyone hope to something, Joseph and Sogil? You can use your microphone. We cannot hear you. You turn on the mic.
Hello, nice to see you.
Good to see you.
You have a light at the backside, so we cannot see your face.
Yes, it's a solar eclipse.
Okay, any comment?
Maybe okay. one more comment, because in November we have been discussing with Hank Rogers, with the International Moon Base Alliance, eventually to organize an event in Hawaii. Yeah, so we'll have a series of simulation in the IC's facility, but also Hank is now building a new dome using radiation material, and we are thinking to make also a kind of VIP workshop there where we can visit the facilities, look at ICs. So November is a time scale which we could also meet again, and it's very well placed for all of you from Korea, from California, and I love to go to Hawaii. It's my second home. So yes, let's also think of something in Hawaii. I was International Moon Base Alliance and also a workshop there.
That's good.
Yes, yesterday.
Professor Park is from the Thailand. You are there, Park Jino?
Ah, okay.
Park Jino 교수? Maybe he's just sleeping. By the way, I should comment Dr. Jang-Geun Lee, and I'm proud of you too. I'm fond of the KHT vacuum chamber, and then you make the very, very progressing, and then you will get the success very good for the big crowd.
Thank you very much.
Only 5 minutes, so I want to talk very quick comment. moon construction or the Mars construction is very important, and then we need to prepare for that. And ISRU is, as we know, ISRU is very important, and we can develop the lunar or Mars simulant, and then we can use it. And then I want to tell you, I was the winning the first prize of the 77 teams, including the folks. What is the ESA?
Foster and partners.
With the Foster and partners, we are the winner, the level 2 phase 2. I'm very proud of our KIC team and then Hanyang University team. And then we want to continuously to develop the more. And I explained about my future plan was not only the spin off, but the spin on, because we cannot develop only construction for the moon and Mars. We should the technology for the Earth planet too. So I make that $10,000 for 4 people with 60 hours for one housing. So that is very, promisable. And also the other enzyme brick is good for. Have you read the Factful List, the book? That says there are level 4 in the world. Level 1 is under the $3,000. Level 2 is under the $8,000. Level 3 is under $23,000 for the GDP. And level 1 and level 2, they cannot obtain the concrete brick because it's expensive. They are using still the brick, the soil brick. So that makes a lot of the CO2 emission for the heating 1200 degree. So one of my technology enzyme brick can make the brick without the heating for the level 1 and level 2 countries, Bangladesh, Myanmar, even India including. So we can now contribute for the space and then Australia too. So let's do it all together. Thank you so much for your.
I have a question. What is the next competition? Because I've been talking with some politicians about the possibility to launch a competition to build a kind of moon village demonstration in some cities. Maybe Paris, maybe Seoul we could do. So is there something we could, like an iconic project where we could build, for instance, a dome and some modules, and it would be good to see if we can do that within a competition or to have a prototype that is first developed and then we try to adapt in different cities.
Actually, the moon race was developed by the Air Force 2 years ago, and so we make using the KST the vacuum chamber for the making brick for the competition. But the Air Force
the rover race. But I was talking now habitat. Do you have a way to build a mini moon base that could be duplicated? So we could do one in Seoul, in Paris, one in California, in a public place, so that that would also inspire the public.
Okay, Bernard, let's do it. Let's do it all together. Give the information and we are in.
Okay, so we start that. Madhu, you do one?
Yeah, Korean time is now 6 o'clock.
In California, there's a lot of land, Bernard, you know that. In the high desert, people are already...
No, so actually, we are thinking both to do something in urban environment for the public and in extreme environment.
Okay, let's do it all together. By the way, thank you so much, everybody.
Okay, thanks.
Thank you for having me.
Thank you.
Okay.
Thank you.
Okay.
Enjoy the Christmas holiday, Jangun.
Thank you very much.
Excellent. Thanks. All the best.
Stay safe, guys.
See you.
Okay, bye.
See you on the moon.
Yeah. Okay.